I think I'll begin. Okay, so my name is Erlebacher, and I'll be discussing today what I call the nascent program in computational science. So why do I say nascent? Because a year ago it didn't exist. Okay, there was nothing a year ago. So, and as I made sure to point out in my abstract, don't expect any fancy research results. This is more like along the lines of what we learned in the last year and what we plan on doing. There's some initial results. Okay, so this is the roadmap. Starting in June 2014 up to now, so a little less than 1 year. So in June 2014, we knew absolutely nothing about the subject, and then this today. Okay, so I discussed how it started. I discussed biology, or at least a part of biology that's necessary to understand what's going to follow. And then I discussed artificial neural networks. I basically have one slide on how we went about going from knowing nothing to knowing what we know today. And then we discussed some initial thoughts about an algebra for polychromy. Okay, so of course the terms will be defined. And then discuss nuclear operation, and then whatever's left over. Okay, so computational neuroscience, I'm quite sure that everybody's got their own definition. There are a lot of buzzwords. Big data, buzzwords. So computational neuroscience is just a buzzword, okay, but ultimately computational neuroscience in general is the province of experimentalists to a great majority, it's dominated by experimentalists, and mathematicians as well, but they're really in the minority, and computational people, well, that's a growing branch. Okay, so really, at the moment, you can view it as a melding between dynamical systems, which basically means a theoretical analysis of systems of ODEs. Neuroscience, okay, that takes care of the biology. Artificial neural networks, because anytime you try to model the brain in a computer, you effectively have some form of artificial neural networks, because by definition you're making some approximation. Okay, so there's anything done on the computer is artificial. And then you got the numerical simulations. And those take, like with fluid mechanics, takes all form. They go from the molecular, the chemical, all the way up to the population of neurons and the entire systems. Okay, so there's the entire gamut. And obviously I'm talking only about a tiny subset. Okay, so Nathan Clark, he had left this place and he came back all excited about neuroscience, went to speak to Richard there, and he basically wanted to know how the brain learns. Okay, so that's like an easy question.
Yeah, really easy.
The question is easy, right? So everybody's been trying to answer that question.
The answer is hard.
And the basic answer is it would take him 40 years of his life to probably not find the answer. But it would take a long time. However, it's a good way to actually try to keep focused, and then from there, so that's what we started with. That was the kind of thing we started with. And so my statement was, maybe you want to focus on. That was his statement too. You want to focus a little more. Okay, but ultimately, what does it mean to learn? Okay, it's like the question is, what's reality? If you construct a robot that you cannot distinguish from a human being, is it artificial or is it real? Right? People have been talking about that kind of stuff forever. Right? So ultimately, if you could actually create some artificial being or some artificial box which emulated the brain, you don't know what's in it, and you pose it a question that hadn't encountered before, and you get a coherent answer, well, under some measures you might say that you've emulated the brain. Under other measures, probably not. Okay, so at the end of the day, the brain is a black box, and the input to this black box are your 5 senses. There might be more. Some people believe there's more than 5 senses, but just talking about the 5 basic senses. So you got touch, taste, sight, smell, and hearing, right? And information from the outside world gets to your brain mostly, I'm assuming, mostly or almost all the way, everything comes through those 5 senses, and they hit on the neurons, on the sensory neurons, and then the information propagates throughout the brain, and from the brain to the body, and then things happen. And then the question is, what makes those things happen? Yes, and of course, and the brain itself emanates its own set of waves, right? That's what you measure with EEG, for instance. Okay, so how did it all start? Well, we started working with 3 young scholar students last June, so that was June and July, and of course we decided to do some cool stuff. So we bought a emotive epoch, which is that device up there on the right. So you stick that on the person's head, and then the idea is that it measures the EEGs coming out of your mind, and they basically said they had software which would allow you to control some game. So we had one student construct this very simple game, and with 2 commands, with difficulty you could make a box go in different directions. So that was actually done. We weren't the first to do that, but we did it. And then also, the whole thing was motivated by a form of artificial networks called the hierarchical temporal memory system, which was created by Jeff Hawkins of, I think, Palm Pilot fame. And this was done about 2007. And this simply, basically, the basic here, it basically handled temporal information. Everything you get into through your brain is temporal, because we had time t, and then a split second later you had time t plus epsilon. Okay, so everything is temporal. It doesn't matter. That's the end of the line. And so the argument here was that you get the brain, it processes things on a small scale, and then agglomerates these small scales to get larger scales, and then agglomerates that to get even larger scales. And at the end of the day, you can actually come up with statements. Well, that's a chair, as opposed to, here's my tiny little pixel that actually hit on one neuron. Okay, so without being able to do that, you can't think and actually do more complex constructs. Okay, however, so we started there. Okay, so here is just a picture of this little epoch measures 14 channels, EEGs. It's a cheap device, relatively cheap, like $500 more or less. So it's not exactly ultra high quality, but it was good enough for our purposes. Okay, so we started there, and just as you pull a thread from a sweater, and then you keep pulling and you got no more sweater, this is like the inverse. We started, I collect papers, right? And because you want to see the big picture, and every time you collect, you're starting in 2007, and then you go backwards, you go forward, etc. And then before you know it, you're going from one topic to the other. Every time we end up with a new idea, we find out it's been done, and you keep going. And then, and then many months later, you find out, finally the articles start referring to themselves, and you're finished. You pretty much arrived. Now we have to read the papers, okay. So you got all these different topics that we actually dealt with, and that emanated from this very first hierarchical temporal memory system. Okay, so let's delve into some biology. The neuroscientists in this room will be bored to death on this small section. However, this is useful. Okay, so neurons, Google images, very useful. Okay, so here are the neurons. Okay, so neuron basically has a cell called, here's a cell body, and it's got a dendrite, it's got a dendritic tree, okay? And that's what's used to actually collect information that actually hits upon the cell of the neuron eventually. And then from the cell of the neuron, information actually propagates through the axon, okay, at some speed. Okay, and then these neurons and this axon and then they connect it to the dendrites of the next neuron through synapses. Okay, so that's the bottom line. So you got the soma, which is basically the cell of the neuron. You've got the information coming along the dendrites, hitting on the soma, and then all this information actually generates signals which propagate down the axon, and then that gets connected to the next neuron. Right, so the synapse is basically the connection that allows you to go from the presynaptic neuron, that's the neuron that comes before, called afferent, I think, and then the information gets translated via processes that actually go from electrical to chemical. Chemical elements get transferred across the synaptic cleft here, and then get transferred to the other side, okay, which is the postsynaptic side. And then this actually gets transformed into a signal which continues propagating down. Okay, I mean, there are many details in here, but I'm really skipping the details that are unnecessary for the talk, and the details that I don't know. Okay. Now, astrocytes is what we're going to be working on. I mean, that's the path we're taking. And that astrocytes is a type of glial cell. So astrocytes to neurons is like the relationship to dark matter. Okay, I'm paraphrasing. I mean, this is my stuff. It's the same relationship as the relationship of dark matter relative to normal matter. In other words, there are many astrocytes in the system, okay, and until not too long ago, people really did not know the purpose. People have known about neurons far longer than, information about astrocytes, okay? And even the function of astrocytes and how they work and how they relate to the neurons is still under intense debate today. People don't really understand the processes, what actually is happening inside the astrocyte. You got many hypotheses, they got models, but they don't really know, okay? And all this is contingent on how good your experimental procedures are to measure. Okay, so that's not unlike supernova. You operate based on what you got, and it's not that much. Okay, so astrocytes, you can read papers which basically say that astrocytes can do pretty much everything. They're involved in everything depending on which papers you read. But for sure, they actually help connect blood vessels. They form the brain barrier. They help connect blood vessels to neurons. So in some sense, they allow nutrients to go from the blood vessels to the neurons, provide energy. But there's been work which basically indicates that they actually involved in various types of medical disorders. Okay, so there's talk about epileptic seizures being related to astrocytic functioning, astrocytic mechanisms. Okay, and what we're more interested in is how do astrocytes affect the functioning of neurons. Okay, so if you look at the previous slide, these little dots correspond to neurotransmitter molecules. Okay, if you have less of this, there's less information that propagates across from one side of the neuron, from one side of the synapse to the other. Okay, and as a consequence, you weaken the signal on the downstream side. If there's no neurotransmitters propagating across, there's no signal on the downstream side. So anything that modifies the amount of information cutting across is going to actually affect the properties of the synapse. Right? So if you notice, there's a way for these elements to actually escape. So my point is, okay, there's ways for the elements to actually escape away and actually be captured by the astrocyte. And there's also mechanisms which allow such chemical elements to go from the astrocytes back into the neuron. And once again, part of it is known, part of it is hypothetical. Okay. So, some time ago, I forget exactly when, there was a concept proposed of what's called now the tripartite configuration. The tripartite configuration basically is a link between presynaptic side, postsynaptic side, okay, presynaptic neuron, postsynaptic neuron, and the astrocytes. This astrocyte actually wraps around the synaptic connection, and they form a tight coupling. I mean, you actually see this in imagery. Okay, not all synapses have an associated astrocyte, but there are many such connections. And so the idea here is that these elements going across, some of them can actually escape towards the astrocyte. This involves glutamate, calcium, IP3, different types of chemical elements. The astrocyte actually, under certain conditions, would actually emit various calcium spikes, which will actually get transformed to other chemical processes, which in some sense would actually come back and return and affect both the presynaptic side and the postsynaptic side. And both together, that actually affects the transmission properties of the synapse. Okay? Now, a term I'm going to introduce right now is called plasticity. Plasticity is basically anything that allows the strength of the synapse to actually change. So for those of you who do neural nets, you can think of the strength of the synapse as being the weight of a node in a neural net. Okay. So let's see if this animation works. Okay, so the idea here, well, if it doesn't work, I'm not going to push it. Right, so the idea here is that different neurons would actually have, different synapses would actually have neurotransmitters, so those little points, actually escape and move towards the astrocyte, right? And under certain conditions, calcium will actually accumulate in the center of this astrocyte, and when it reaches some threshold, this calcium will spike. There will be a spike of calcium, and then neurotransmitters will be fed back to all the other neurons and affect the synapses, right? So the idea is that all these neurons will affect this astrocyte at different times, and at some selected times there will be a spike that will affect all the neurons that are actually connected to this astrocyte. Okay, that was hypothetical, right? In recent times, the people we're collaborating with are finding that that is not necessarily happening that way. Okay, that the center of the astrocyte is maybe not quite as important as people thought it was. Okay, let's stop this. Okay, now, so that was the biology. That's like biology or 100. We're not even at the 101 level. Okay. Okay, now prototypical models, right? So you take this biology and now you want to model this somehow. So the modeling in the neuroscience world, correct me if I'm wrong, okay, but pretty much started with the model of Hodgins and Huxley, right? So they basically based this on some giant squid, and they modeled the neuron as a membrane, okay, and they basically use electric circuitry to actually write equations for this, for the physics of the membrane of a neuron. Okay, so I'm going to show the real basic equations in a minute, and for in a lot of models, they consider the neuron as a single point. So when you consider a neuron as a single point, you neglect the spatial structure of the axon of the dendrites. But it so happens that spatial structure has importance. Spatial locality, in the brain has a big impact. You got propagation delays, you got induction effects, and you got all kinds of things that can happen. But in many cases, it's neglected. Right, and then of course you got single, multiple, and all kinds of models, that you can create, depending on the level of complexity. You can also go down to the chemical level if you're interested. Okay, so not that I'm going to discuss this. These ion channels, can become arbitrarily complex. Okay, and so the membrane in a neuron, or the membrane, the sheath, if you look at the axon and the dendrites, they all have a membrane, which wraps around this way. And this membrane is like a lipid layer, right? And in this lipid layer, you've got various ion channels. And these ion channels allow things like sodium, calcium, chloride, potassium, to actually propagate depending on the concentrations inside and outside. Right? And these concentrations create electrical gradients and are actually responsible for the voltages. And so depending on how these propagations occur, you can get different voltage effects, inside the axon, dendrite, etc. Right? And these type of ion channels, they occur everywhere. And the ion channels are very particular. Typically, they're very particular to one particular kind of chemical element. And they play many roles. I mean, there are papers which are titled Zoo of Ion Channels. That should tell you everything. Okay, so here's all I want to say about the Huxley equations. Okay, so you have an electric circuit, and so the lipid membrane forms like a capacitor. You can view this as a capacitor, and across this capacitor, you've got multiple ion channels. And this arrow basically means variable resistor. Okay, and so this electric circuit is modeled in terms of conductances. Conductance is one of the resistance. And this conductance, you've got these different terms for the different currents, for the different types of elements, because they go through these specialized ion channels. And these different conductances are a function of the properties of the ion channel. So these ion channels can open and close. If they open, chemicals can go through. If they close, you've got blockage. Okay, and that's controlled by parameters like things like M and H, on which this depends. And these parameters have their own set of equations. Yep?
So you have like sodium, potassium, chlorine, and calcium. Are there any other elements that could go, or are there just the four of them?
My guess is it's more. And I can tell you I do not know what they are. Somebody could answer? Nathan?
There are way too many of them.
Okay, so what happens is, so what happens is that voltage actually grows in the soma, okay, until it reaches some kind of threshold, and at which point there's a spike that occurs. So you can view this spike for practical purposes as a soliton. And this spike, because of the properties of ion channel, will propagate down the axon and eventually hit on the synapse, and then will go across the synapse, and then whatever happens, happens. And then the signals from many neurons actually hit on the next neuron, and under certain conditions, the other neurons will actually spike. Okay, and so then you can get all kinds of effects. Now, depending on the parameters of these equations, or many parameters, you can get different kind of spiking behavior of the neuron. So the neuron could spike, and then spike a little later, and then spike a little later. You get tonic spiking. Okay, you can actually get bursting, so you don't just get one spike, but you get many spikes that occur, and then it stops, and you get many spikes that occur. So anyways, these are the spiking patterns that you can get out of the so-called HH equations, depending on the parameters. Right. Now, it so happens that if you want to actually code these equations efficiently, you look at the last line, it says Huxley, it takes like 1,200 flops, 1,200 floating point operations. Okay, so that's perfectly fine if you want to, even then, if you want to do one neuron or maybe 5 neurons interconnected, and so you got a network of 5 neurons, each one modeled by these equations. But this is not good if you want to solve 100,000 or 10 million, because your computer's going to croak. That's a technical term. Okay, so people have actually created a range of models, most of them called integrate and fire models, right? Which I'll explain in a second. And these different models, what you've got listed here horizontally are all those different spiking behaviors. Okay, and some of these models can handle different types of spikes. And these different models basically have different levels of complexity. If you look down, you've got 7 flops, 7 operations. This is great. However, there are many minus signs, which means it doesn't matter how you apply the model, you cannot model this kind of spike. It cannot be done. But if you're not interested in that kind of spike for your experiments, then you take a cheaper model. So the model you use should be a function of what you want to do. Yeah?
So the different spiking behaviors, you said were a property of the model, right?
Yes.
Is that a property,
I'll explain.
a real property too? Like, is it that experimentally,
a lot of the stuff is
spiking
technical. Okay, so let me explain. Let's assume you have an equation which depending on the initial conditions has 5 specific dynamics. And then you do a model, and based on the different initial conditions, there's only 2 dynamics, and the other 3 dynamics are not there. I mean, that's what it is. So those dynamics are verified experimentally, but they're only approximations. But keep in mind that these Hudson equations are also approximations. They just are better approximations, but they're approximations nonetheless. Remember now, they're modeled by electric circuitry. You'd have to go through the chemical details of the chemistry, take into account the very low molecular dynamics in the ion channels if you wanted things to be exact.
No, what I meant was, are there features of that Hudson model which are spurious to the model, and hence a negative sign is not?
Oh, the features of the HH model. No, that I don't know. I don't know the answer to that. But they've been very well verified. But I can't answer that question specifically. Oh yeah, so the best model is the one by Izikovic, the one in the middle there, 13 flops, and it can handle every one of those spiking behaviors. So it's sufficiently close to the minimum of 5 that it's a model which is reasonably popular. Okay, so now let me explain. This is the kind of spiking result you would get if you solve the HH equations, which means that you got some kind of potential in the neuron, and the potential grows depending on based on its inputs. Every time there's an input spike, it grows slightly. And at some point, it reaches some kind of threshold potential, and then it grows very fast and then decays. So that's called depolarization, and that's called hyperpolarization. Okay? Now this is very, very small in time. I mean, this is like 2 milliseconds, let's say. Right? Tiny, very tiny time scale. Here is the result of of those equations on the left, which is that model I just told you, which can handle all the spiking behavior. And this is the model. And the way it works is, it cannot handle the spike in a continuous fashion. Okay, that's the price you pay. What you've done is you've actually condensed all of this to a single delta function. Right? And as a consequence, when you solve this, you simply say when V reaches a threshold, reset the voltage down to the base voltage. So once the voltage reaches some threshold, simply reset it. And so you simply make this time go to 0. That can create complications numerically, but it can also greatly speed up your numerical calculations. So not only do you have less flops, you can have larger time steps.
So Gordon, what
Yeah.
is the meaning of the particular terms in those equations? Do you know?
Okay, no, I cannot interpret. I mean, this is, okay, so this is a, this is called like an associated verb. No, I do not know. This is like an input current into the neuron, this term. That can be viewed as the potential of the neuron. And this can be viewed as an associated variable which is meant to affect the dynamics. The fact of the matter is these equations to some degree can be reduced by multiple time scale type expansions and association of variables, via dynamical system theory. And so you can do this model reduction. And so sometimes the models lose their physical significance. But you can always transform back if you know the transformation. And they do. Now these equations are often used, to do artificial experiments to get a feeling. Okay, so some important concepts are, which I'm not going to discuss in detail, but obviously spiking dynamics, right? These days, it is pretty much believed that spiking contains crucial information, and plays an integral role in how the brain functions. You cannot simply ignore the dynamics of the individual spikes. It used to be that people average the spikes over time to actually get information, but it was found that there are many things that it doesn't explain. I can't tell you offhand. But individual spikes are viewed as very important. Second, propagation speed. It takes time for the spike to actually go from one neuron to the synapse. And there's a range of times, like between 1 millisecond and 40 milliseconds, give or take. Okay, and yet many artificial neural networks that read in the literature, you assume that propagation of information is infinitely fast from node to node. In fact, you just solved one big gigantic system of equations that actually solve for the neural network properties. And then there's plasticity. Like I said, anything that changes the strength of the synapse is plasticity. You got to make at least 4 different kinds of plasticity. Okay, and those obviously play a role, and it's pretty much, I think everybody typically believes that plasticity plays an integral role in learning. The stronger the connections between neurons, the stronger we'll actually memorize and be able to repeat somehow. Okay, so how did we learn? Okay, it's not like you have tons of courses here. So online courses played a big role. Course A, there are many free courses online. We could take, and we took several. Okay, two of my students, Nathan and Evan, take courses from Richard Bertram. Okay, and then papers. We have weekly meetings here. Richard came to a couple. Okay, and so here we talk about all our crazy ideas. And then, of course, we question everything. You don't believe anything you read because, okay, that's a hard lesson to learn. And then, of course, we code up, we write codes, some codes into demos. So I'm just going to show you one example of a demo. Okay. So if I go to science. Oh, not, yeah. Python, function. Yeah, well, that's never happened. Okay, so I'm going to continue. Okay, don't understand. Especially since it was tested half an hour ago. Okay, so what we've done is we've written several Python programs that actually, we've written several Python programs that actually get a better understanding of these equations, because looking at these equations and understanding intellectually is one thing. But if you want to speed up the learning process, we want to be able to control everything. We want to control the input current, the time scales, the numerical time step, how long we see the data, look at the phase plane, and then change everything, and we can actually see the spikes occur and disappear in real time depending on the parameters. And that really allows you to cement what you've learned. So every time I would read about a model in a paper, you know, I mean, there are several cases where I would actually program such interactive things, you know, to get an idea of what's really happening. And it also helps debug your code. Okay, so now on the left, we got reality, that's your brain. And on the right, you got a neural network, you got whatever's artificial on the computer. Okay, and the idea is to make the output of the right-hand side match the output of the left-hand side. Right. Now most algorithms, you got to view this as a black box. Right? Your brain's a black box. You got input, that's with your senses, and you got output. And for thousands of years, it's functioned perfectly well without anybody knowing what happens inside. Okay. So, and when you do any kind of numerical scheme, or you write a function, your function's a black box to anybody who did not write the function. Right? And so what you're trying to do is reverse engineer the brain. Okay, so now whirlwind tour of artificial neural networks. Okay, so the artificial neural networks, of course, was biologically inspired. We often have discussions, okay, Nathan wants to do biologically inspired stuff. I don't mind doing purely artificial stuff. The question is, there's a fine line between the two, because everything on the computer is artificial. Okay, so initially, okay, the neural networks have the following basic computational unit. You've got a bunch of inputs, and these inputs have weights. Okay, and so these are my different input channels. You can view this as your senses. And they actually all get added up, right? You've got some kind of linear combination, and they get fed into some kind of nonlinear function, which is often a hyperbolic tangent or an exponential of some kind. Right? And then this input, okay, and so this input gets transformed, and then this becomes one of these inputs into some other node. Right? So this is not unlike what happens in a neuron, but it's greatly simplified. Okay, so having this computational unit, this basic computational unit, here is a series of more and more complicated neural networks, you know, and kind of what they do. Okay, so the basic neural network is where you have, you've got a series of inputs, you've got a series of outputs, and then you've got hidden nodes. Hidden nodes are the ones not accessible. That's inside your brain. This is your EEG, and this is your touch. Okay? Now, you can put an arbitrary number of linear nodes, and for all practical purposes, this result is a linear combination of linear nodes. And we all know you can take a function, if you've got basis like sine waves or cosine waves, you can represent the function by an arbitrary linear combination. And under mild restrictions, any function can be written as such a combination. Which means that under mild restriction of integrability or whatever, okay, a neural network of this type can approximate any function. I mean, that's where it comes from. Okay, so far so good. Now you notice that the information propagates from left to right only. Okay, so here's a case where, well, I'm just repeating what I said. You can approximate any function with one layer. Okay, now here you've got a network where I've got multiple layers. Okay, so here's my input. This inputs get fed to some initial layer. The output of this initial layer get fed to some second layer, and then third layer, then a fourth layer, until eventually you get to the end. Right? So that's just a more sophisticated network. And once again, you can represent any function, but it so happens that a given function can be represented with a lower number of nodes than if you only had a single layer. So that will be equivalent to calculating, instead of writing a Fourier series, you would write sine of omega times sine of omega times sine of omega. You'd have function of function of function of function as opposed to a sum. That's how synthesizers are done with very few circuitry. Okay. And this, when you basically have many hidden layers, is what's called deep learning. So when you see deep learning in the literature, that simply means you're dealing with a neural network with many hidden layers. And those deep learning networks are the ones which basically at the moment hold the record for recognition of patterns, where you can basically feed in millions of pictures, you know, and they will actually recognize things ultra accurately. Those are the kind of networks. And there's all kind of, there's another theory on this too. Okay, however, the brain is not feed forward. Here before the information only went from left to right. But the brain, the information does not go from left to right. It goes in any which way. Maybe not quite, but it goes in both directions. So here's a case where I've got an input, it goes to the first layer, this neuron gets fed to itself, or the neuron goes to the second layer, and then here it may go laterally, and then at some point, when you get to the output, maybe it gets fed back. Okay, so here's another feedback. Okay, so the information could go in both directions. And so you can have loops, you can have all kinds of phenomena. Now, in the same way that a feed-forward network can approximate any function, a recursive network can approximate any set of any number of ODEs. In other words, a recursive neural net can approximate any dynamical system. Okay, which is not inconsistent with the fact that neurons are often modeled by biologists as a set of ODEs. And a set of ODEs can be modeled by some arbitrary recursive network. So at least you got some level of compatibility.
Can I ask, so the previous model, you know, so all they went from one set to another. Everything had, so you know, there was input, everything would, you know, at one time set. And here you get a time dependence because, you know, the output is coming out at different times, right? Because, you know, you could have, like, I can trace a path from a red to the thing.
Yes, actually what you do
number of steps.
is you take, when you take these recursive, you can actually break this, okay, and you can actually model this by taking, by multiple feed-forward networks put end to end. Okay, I don't think I want to go beyond that. But what is true is that the loops that are formed in here actually are partially responsible for the time dependence of what's happening. So you could view this, so just imagine that you take a set of ODEs and you discretize with your favorite numerical method, and you basically say un plus 1, right? The solution at time n plus 1 is equal to solution at time n combined with whatever operation, right? So you can see that any discretization of your differential equations can be transformed to some kind of network like this, where you replace un, when you write un plus 1 equals un plus delta t un, you simply replace un plus 1 on the left and you make it into a recursive loop. Okay. And reservoir network, okay, I'm going to speed up slightly unless you want to stay till 5, which is fine with me. Okay, and that is, this kind of network is very interesting. You've got a series of inputs, and you've got a series of outputs, and then you've got a big black box in which you've got some kind of mishmash of a recursive net. And the advantage of the reservoir network occurs when you actually train the neural net. Many neural nets are trained, and you've got to actually calculate the weights based on some kind of, you're doing supervisory learning, okay? And so you got to calculate the weights. In the case of the reservoir network, the calculation is much, much cheaper. Okay, so that's all I say. And I say that the reservoir networks, because of the cycles, have the potential to store information, okay, and they have the potential to actually work with temporal data, and the storage of information can actually be related to storage of information in your mind. When you actually remember something for a couple of minutes, that can be viewed as a loop in a reservoir network. Okay, that's. Okay, now, in all these networks, what's been neglected? There's nothing about propagation speed. Information goes from one neuron to the other at a fixed speed, infinite. Okay? And there's no spiking. There's no concept of spiking. I mean, all information gets to the neuron at the same time, and then it's your nonlinear function. There's no threshold, no nothing. And, okay, so that's it. Okay, and most neural networks are supervisory in training. Okay, even the deep learning networks. Okay, the brain is non-supervisory. Nobody's there showing you a picture of something, and you answering yes or no and training your neurons. Your professor might, between ages 0 and 1. That's not happening, not really. Okay? Now, all the previous networks can actually be enhanced to add spiking and propagations between nodes and weight changes via plasticity. Okay, another concept which is important is synchronization. So that's going to play more of a role. So in big networks which are apparently random, you can actually measure sometimes entire groups of neurons which are seemingly unrelated, which synchronize and spike at the same time. Okay, so how to explain that? And there's a huge literature on that as well. Okay, and then there's balance. There's so-called inhibitory and excitatory neurons. Okay, some neurons amplify signals, some neurons inhibit signals, dampen the signals. There's like a ratio of 5 to 1, you know, 4 excitatory to 1 inhibitory. That's the rule of thumb. None of this is true. Okay, now, starting with, syn-fire chains. So, under certain conditions, if you notice, sometimes there are birds out there, right, and they always make the same group of sounds. Right? And then it gets replayed, and then it gets repeated over and over again, absolutely identical. So that would kind of imply there's a particular sequence of firing in your brain of the neurons that are repeatable. Certain series of events in your brain that are occurring repeatedly. Otherwise, the sounds created by the birds, I mean, it's hard to believe they would be absolutely identical. Okay, so that from there is kind of born the idea of syn-fire chains. And syn-fire chains goes like this. Okay, so you can ignore the color. And here's a multi-layer forward network. 1 layer, 2 layer, 3 layer, 4 layer, 5 layers. So the idea is, if you imagine you got something like that inside your brain, and all these 3 send a signal, this guy sends a signal to these 3, this guy to those 3, okay, and these 3 are strong enough to make this guy spike, that guy's going to spike, that guy's going to spike, and these 3 spikes, again, are going to send the same exact signals, and then these are going to spike, and those are going to spike, and those are going to spike, and so those 3 spikes are going to propagate throughout the network. And such propagations have been to some degree measured, okay, but indirectly, okay, over periods of like 300 milliseconds, I mean, which is fairly long. Okay, and this is a plot, kind of a plot we're going to see later, where you have time on the horizontal axis and you got layer on the vertical axis. Okay, so these are the 3 spikes, okay, and you get a dot when the neuron spikes, and you get nothing when there's no spike. Okay, that's called a raster plot. Okay, so you can see here at early time, the first 3 spike. First 3. You see the red and the red dot here. Next time, the next 3 spike, then the next 3. So you can see the spikes actually propagate, you know, along the forward network. But it so happens that if you do numerical simulations, depending on the conditions, depending on the properties of the initial spike, because you say the spike, all the spikes occur on the first layer within a span of, let's say, 1 or 2 milliseconds. They don't occur exactly at the same time. Okay, well, depending on the parameters of the system, the spike's going to remain coherent, or the spike's going to actually lose coherency. So it's not, you know, completely trivial. And the identification in real beings is not trivial either. It's not that it's been 100% corroborated. Okay, however, for the most part, the delays are not constant in the brain. If the delays are not constant, you can imagine it would make it much harder for these syn-fire chains to actually create. So it's possible that such feed-forward networks occur in selected parts of the brain, you know, and not in others. So if we take networks now where the delays are not constant, what happens? Well, there are certain kind of constructs which a few people have written about, okay, called what they call Pelicanus groups. So Pelicanus group is a particular firing sequence which occurs in a spatial temporal sense. So instead of having the firing of 10 neurons happening all at once, it's like firing here at a later time, firing here at a later time, firing here at a later time. So the firing is spatial temporal, right? But the sequence is repeatable. Okay, so the same way with the birds, the sequence is repeatable. It's just that you get very few neurons spiking. You no longer have 10 neurons spiking at once. You got 1 neuron spiking here, and then another neuron spiking a little later, okay, and a little later. And so that is Pelicanus group. So when we started reading about that, you know, at least I remember saying, hey, Nathan, this is really cool. You know, you could do all kind of interesting things, because the guy who wrote about it was making use of this and linking it to memory. And understanding how memory works is one of these things which is not really well understood yet. Okay, so what I'm talking about now is entering the realm of even more hypothetical than before. Okay. All right, so some research hypothesized that the sheer number of Pelicanus groups makes them a candidate for storage of memories. Right, so Richard, this is hypothetical, not real. I know this initially. So here, so let's take a picture out of a paper from Izikovic, okay, which shows like a pentagram, right? You got 5 neurons with some kind of complicated structure. You could see it's recursive, right? You could see some links go in both directions. And on each link, there's like a number written. 4 milliseconds means it's a delay. So information leaving neuron number 5 at time 1 will reach neuron number 2 at time 1 plus 4, which is equal to 5. Okay? Now the idea is if you have two spikes, I mean from an idealistic point of view, if you got two spikes hitting on a neuron at the same time, we will say that that spike will propagate further on. In reality, the number of spikes that have to hit a neuron at the same time can range from 50 to 1,000, depending on the kind of neuron. Right? Those are the EPSC, you know, for the biologists. Okay, so the idea is, and what you see drawn here, there's no need to go into detail, but once again, it's time and neuron, and what you see here, this neuron emits a spike at time 0, propagates to this neuron, which hits at time, let's say 5. This also goes to this neuron, which hits at time 7, you know, and every time two spikes hit a particular neuron, the spike propagates. So from this diagram, you can actually construct these different individual polygonous groups, right? And as the number of neurons becomes higher, and as you increase the number of connections necessary to propagate a spike, one can easily imagine that the number of polygonous groups will go to infinity really fast. I mean, will grow exponentially. I mean, just looking at this, it's not hard to imagine if you multiply all these numbers by 1,000. Okay, it's crazy. So the kind of question some people have tried to answer, well, first of all, what I'd like to know is, if you take a simulation in which you've got synth-fire chains, right, and now you change constant delays and non-constant delays, it should somehow transform to polygonous chains. And how does that transformation occur? Well, I find that interesting. What are the statistics associated with polygonous groups? How many are there as a function of different parameters? You know, and then how are polygonous groups affected by recursion, which greatly complicates things. Okay, so some questions. So if you take G, the number of polygonous groups that exist in an idealistic sense, which is finite, and then the question is, how does the number of polygonous groups depend on the number of neurons? How does the number of polygonous groups depend on the number of connections required for the neuron to fire? What is the effect of recursion on the properties of, well, I kind of said that, right? And then you could ask, plasticity. In real life, there's plasticity. So how are the polygonous groups affected by plasticity? Do they disappear? Do they strengthen? Can you talk about the notion of stability of a polygonous group? What does it mean to say that a polygonous group is simple or complex? Okay, so Nathan, of course, being idealistic, okay, he said, okay, would it be cool if we had some kind of algebra, right? We want to. He basically took somebody's paper, this guy Miller. He wrote this paper in a very idealized sense, and basically modeled numerically much simpler equation than what we have now, but modeled numerically, you know, polygonous groups. And you know, and it was fast, and you know, he got results, you know, duplicated the results of the paper pretty much, and then said, wouldn't it be cool if we had some kind of algebra? An algebra would mean what? I think I asked some questions here. Well, later. Okay, I asked some questions, and such as, given a polygonous group, okay, could you decompose it into simpler polygonous groups? Or given a neural network, could you decompose it in some way that you could actually deduce results in simpler manners? So for anybody who knows about group theory, you could talk about irreducible groups and various other things. Okay, so here's a little bit of what he did. This is maybe 2 months old. Okay, so this is really recent. So take a simple case. Here's the simple case with 3 neurons. So you go from 1 to 2 with a delay of 4, 2 to 3 with a delay of 1. Okay, so you get the idea. So a neuron, you pick 2 neurons, which I'm going to consider to be anchors, and the neuron 1 fires at time 1, and neuron 2 fires at time 2. And this neuron would actually hit on this guy with a delay of 3 minus 2, which is 1. And this guy would also hit on this neuron with a delay equal to 2. But because this spike left earlier, they will hit at the same time. So because you got 2 spikes input on here, that guy will spike and will propagate down that way. If these 2 neurons, if these 2 had hit 1 millisecond apart, then the spike would not be propagated. Okay, so the further it propagates, the larger the polygonous group. Okay? Now, if you're going to do an algebra, you've got to establish symbology. Right? So the symbology says that the polygonous group is solely determined by the first 2 nodes. The minute these 2 fire in a given network, everything that follows is predetermined. So if everything is predetermined, there's no point recording it. Okay, so the polygonous group will be identified only by these two neurons and when they fire. Okay, and that will be annotated as P1 is a collection of two numbers in a set. Okay, the first number of the pair is like the neuron, the second number is a delay. So neuron 1, delay 1, neuron 2, delay 1, that represents these two, and once you got these two and the properties of the network, everything's predetermined. In the real network, of course, the strength and the delay stay fixed for the most part, but the plasticity and the strength of the synapses change, and that would actually affect things. Okay, but we ignore all that. And here's a case where I take 4 neurons, and of course, all these data is contrived, okay, that's understood. So with these 4 neurons, you can get, I'm not going to go through it, but you get these 2 Polygonous groups. In other words, if you start with these 2, this is what happens. If you start with those 2, that's what happens. You know, I'm not convinced there are no more, but maybe he's right, I don't know. Okay, but there are at least 2 for sure. Now, okay, and they annotate it this way. Of course, this is still heavy annotation. So, I'm going to say, think about it this way. If I got 2 neurons which fire at time T1 and T2, okay, and they create some Polygonous group, if both those neurons had fired a fixed time earlier, a fixed delta T earlier, like at time T1 minus 5 and T2 minus 5, I'd get exactly the same results. That's pretty clear, because this whole Polygonous group depends on delta T's, okay, on the delays, okay, from the time the first neuron spiked. So as a consequence, this relation holds. The Polygonous group P1, I can subtract an arbitrary time from both these times and get exactly the same group. Okay, and as a consequence, one can actually simplify the notation because I can say T1 minus T3 equals T1, so the second element of the first node could be 0.
Yeah, you
Okay.
have a typo in the last.
Typo, I finally found a typo. Yeah, where?
T2 minus T3.
Hey, Nathan.
My fault. I was supposed to-
Where? It doesn't matter. Okay,
4 comma T1 minus T3.
okay. Oh yeah, you're right. Okay, good. Okay, so now let's talk about a network. So I'm going to draw a raster plot. Remember now, raster plot is neuron number, time on the horizontal axis, neuron number on the vertical axis. So here are the 2 neurons. Here are the 2 neurons that fired. Okay, the 2 neurons in the group. Those are the neurons, and I put a 1. Okay, let's not worry about that. Now, the translation invariance, the time invariance of the Polygonous group, it says take these 2 and simply move them here, the same Polygonous group at a later time. Because the Polygonous group is really, you draw the whole neuron structure and you can simply light up whatever neurons form the Polygonous group. It's like stars. Okay? When you look at stars, you don't see the time axis. So here we're drawing the time axis. Okay, so now I'm skipping, okay? So here is a definition of a neuron, a mathematical definition of a neuron, which a neuroscientist will cringe, okay? Doesn't matter. Okay, so here we have a neuron, and I'm going to basically say this superscript I represents the neuron I'm dealing with. And what this represents is the delays from this neuron to every one of the other neurons. Right, so one neuron, in principle, is connected to everything. Of course, some neuron pairs don't have any connections, in which case I put 0. So the timings here is either 1, is a number of seconds, of milliseconds, or 0. If it's 0, there's no connection. Okay, so that's a definition of a neuron. Okay, so, yeah, I'm not going to push beyond because you could see the time and I knew this was going to happen. Okay, so, but the point is, we also define the notion of a basis function. Yeah, don't go right away and say it's not E1 equals 1, 0, 0, 0. Oh, it actually is defined as 1, 0, 0, 0. But we haven't even established yet that these are vectors, okay? And whether we can or not remains to be seen. However, what I've definitely introduced already is a matrix type structure, which is like the raster plot, that's a matrix kind of structure. We've introduced a vector-like structure. I say like because it doesn't formally yet satisfy vector properties, and it might or might not. I'm hoping that we can change things in such ways to make them satisfy a vector property. And we also have the concept of a basis neuron. Now we already have a time shift operator because you added minus T3 to everything and you got some invariance. And you've also got other operators, plus and minus. We can do things already, okay? So now, research objectives. Whether it's possible or not remains to be seen. Since a neuron has n components, it's conceivable that you may be able to add a vector or partial vector structure onto that. What's the advantage of putting a vector structure onto anything? Well, once you got a vector structure, you got a norm. Okay, once you got a norm, you got a metric. Once you got a metric, it means you can compare distances. Once you can compare distances, it means you got order, which means something can be greater than something else, or more complex than something else, or whatever. Okay? You've also got a matrix, which is basically the network. Okay, except doesn't satisfy the properties of a matrix. If it did, okay, or if we could even make that network represent a vector, then one can define spaces of networks. Once you got spaces of networks, there are other mathematical tools one can use to do more things. Okay, once you can do this kind of stuff, then you got the possibility of taking a network and breaking the network up as a linear sum of irreducible networks. Okay, and once you can do that kind of stuff, maybe you can actually do mathematics and establish, or do it this way, you could establish the notion of equivalent networks. Take two networks which look different, but if you reduce them back to the same irreducible representation, they really have the same properties, even though they might look different. For sure, we know one thing for sure. If you take a network and it's symmetric, we bilateral. If you take a network and it's symmetric and you flip top and bottom, the particular groups probably will be the same by symmetry, which means that should somehow be reflected in this algebraic structure. How? We haven't gotten that far, but I'm just saying. Okay? So, and once you got that, you got invariances and you got Lie groups and whatever. Okay? All these things are possible. Group theory becomes possible if you can do some of this stuff. If you can't, then you're stuck. Okay, but Nathan already did what I thought was impossible, so I never know. Never know. Gotta keep an open mind. Okay, so so that's that. Now, so recently, Nathan and Joel is sitting right there. When we figured at this point, well, Joel is a neuroscientist, okay, but Nathan, we figured at this point he understood enough we could actually go places and maybe have a hope of understanding, let's say a third, okay, and let's say or a fifth, okay, and so he went to the Symposium 2015 conference, which was down South Florida in Jupiter. That's the Max Planck Institute. Didn't know there was a Max Planck Institute. That was not in Germany. Okay, and so that was attended by those two, organized by these guys. And while there, he basically did not fail to impress a researcher by the name of James Schumer and his postdoc, who are working on astrocytes. They've got some, what's it called, a two-photon fluorescent imagery. Okay, some of the highest resolution pictures of astrocytes. 256 pixels across an astrocyte is large in the scheme of experimental measurements. Okay, and those experiments have already shown that, okay, this is James. Okay, and those experiments have already shown that some of the assumptions that people have had in terms of astrocytic, let's say, biological phenomena may be incorrect, or at least are incomplete. Well, the fact it's incomplete should not be a surprise. Okay, but anyway, the point is there could be calcium generation mechanisms that occur in the processes of the astrocytes. The astrocytes, if you recall, look like starfish, right? And the branches of the starfish, they call branches or processes. Okay, that's a synonym, right? And it so happens, many of the pictures always showed the astrocytes of having a couple branches like starfish, and maybe the branches having secondary branches. But in reality, they're finding those branches subdivide arbitrarily thin to the smallest resolution the cameras are capable of seeing, and it kind of resembles, like a fractal, a multiple layer fractal. Really fine, so it's really not clear what happens at the outer reaches. And and so they've got experiments where, a long time ago, this was in 1950s, Hubble, when was that, 50s? Okay, they measured basically the response of neurons to orientation. So basically, you could have bands that would actually move away from you or towards you. I don't know exactly how the experiment worked, but at different angles. Okay, and depending on the angle, different neurons became activated. Where they're finding that the same kind of phenomena occurs in the astrocytes, that certain sections of the astrocytes, okay, get activated depending on orientation, and there may or may not be a link to the adjoining neurons. Okay, so they're finding this out, things that have not been known. And so they actually have video. Here on the left is actually an astrocyte. So this is like 256 pixels. And so they got these video recordings where they run one frame every quarter second, and they basically show an orientation to a ferret, an orientation of a moving band, and then what they do is they record for 32 frames. That's equal to 8 seconds, and then they change the orientation. They record again, then they change the orientation. And they go all the way around, and then they got these videos. So they gave us a set. This was only 2 weeks ago. They gave us the set. The conference was 3 weeks ago, right? Something like that, 4 weeks ago. So they gave us a set of 540 frames, right? And then I said, these are their slides, okay, from their presentation. So I said to them, okay, let's see what we can do, just fool around. We have to start duplicating the results and we'll move from there, okay? I mean, this is our big chance to learn a lot about experiments that are on the edge. Okay, so here's like a picture. This is like a picture. I took the average of all 540 frames, so you get some kind of average. Those frames, what they're measuring is calcium concentration. So all they've got is calcium concentration at high resolution. Okay, so this basically shows you the astrocyte. This is hard to see on a flat image. This shows you at the center of the astrocyte, the calcium ion. They really have very strong peaks compared to everything that's around. And here you can kind of see the branches. Here, 1 branch, 2 branch, 3 branch. And here's like probably another astrocyte. Add the word probably to everything I say.
You're
Okay.
probably right.
Thank you. I'm recording my talk. I'm going to cherish this forever. Okay. So then they've actually performed ICA, okay, independent component analysis. Okay, so you start by doing a PCA. I started with PCA, of course. I'm reading up on all the things I don't know that I should know. And so here the PCA is meant to actually maximize, basically to isolate the different directions of maximum Gaussianity. Okay, so you're basically looking at the eigenvectors of the correlation matrix. Okay, and then so these are the eigenmodes. And then what they do is they whiten the data, or I assume they do, which basically means you change the transformation of variables so all the variances become equal to 1. Okay, so now you got a covariance becomes a sphere. And now you apply ICA, which basically means you isolate the regions of maximum skewness. Okay, so so you basically like do an SVD combined with a rotation of V, one of the matrices, in order to maximize or minimize. You want to minimize correlation between the different variables. Okay, that's what you want. Okay, and then that's how they're able, and from there they actually generate the segmentation plots that you saw in the previous picture. Something which I do not yet know how to do. Bought a bunch of books already. Can get at my house in a couple of days. Okay, but of course I've got them to ask questions. But they're not mathematically minded. Okay, so we're not on our own, but I'm tapping into people who might know this stuff. Some people in this department have been tapping in on their knowledge. Okay, so that's as much as I want to say. And then the last thing is that I've got one student, Juan Llanos, who just joined us, and he's playing around with interaction devices. Okay, so here you see an Oculus Rift, and you've all seen Oculus Rifts. Okay, and on this Oculus Rift, you can actually see this, which some of you will recognize as a leap motion. Okay, so we've got this. So the Oculus Rift allows you to look at VR, virtual reality, and the leap motion is like a little device which is typically in front of your computer and allows you to actually move your hands, and the computer will track this with infrared, and then you can actually manipulate things on the screen. Like I could basically do this. You've all seen your favorite shows like Minority Report, right? So the leap motion allows you to do that in some sense, okay? And so the idea here, okay, this is work that he did. I wanted him to actually program this stuff, but not simply use a software that Microsoft gives, but actually write his own software. Okay, and the idea here is you can imagine this to be 3 neurons of a neural network. Yes, it's a primitive brain, but more like an amoeba or something. Okay, and so, and you got 3 connections. And what I would like is to put a back end on this, which would be, let's say, a GPU cluster-based neural simulator with whatever physics we want to put into it. And then the idea is that the output, you'd have output, right? So your output would be some kind of signal, which would be like an artificial EEG of some kind. And the idea, from didactic purposes, that I could actually go now and take this neuron and move it, and if I took spatial activity into account or delays, the signal would actually change in real time or quasi-real time based on what I was doing here. Or I could take a block from my block pile and bring it here, change connections. In other words, construct and modify simple brain configurations and see the output in real time to get my intuition. So this would be like a 3D virtual version of the simplistic slider version of those differential equations I showed earlier. Okay, so ultimately that's where I want to go. But of course, by the time he's finished, the computers would have sped up dramatically. So we'd obviously be able to do problems larger than we can do today. And that should do 4:30. I'm done. Questions? No, it's totally clear, actually.
So just for this slide, so what's the motivation for you to try to manipulate your neurons with this?
Oh, honestly, having fun. But more than that, from a biological point of view, nothing really. Okay, but honestly, if moving a slider allows me to actually get a better feel for the solution of a differential equation, it seems to me that understanding, look, you got neural networks, and you start drawing complicated networks, even if you had maybe, let's say, 500 neurons. In my view, drawing the 500 neurons on a 2D plane will make you understand less what happens than if you see them in a 3D configuration. And the fact of the matter is, your neurons are placed in a 3D configuration. So for instance, you had the V1 to V6 layers, that's a 3D configuration. You've got other 3D configurations. So once you start looking at the output, and you basically start having more realistic models, maybe 5 years from now, okay? And you could start moving, maybe you move layer 1 closer to layer 6. Let's assume you had a good model of layer 1 to 6. And you move them slightly closer together in 3D, which is more intuitive than in 2D, and you saw what was happening in terms of the signal, maybe that would teach you something. Maybe not. Probably not, but maybe. But at the end of the day, I'm having fun. And computer-human interaction is everything these days. Yeah?
How about you were talking about the delays a couple of times, the delays between those. So those are they known to be kind of like constant throughout? I mean, usually, I mean, can you assume them to be fixed? Or
no.
Are they known as
you
statistical
cannot assume them to be fixed. I mean, yes, you can, in the sense that many people, the whole field of neural networks, which has been very successful, is based on the fact of fixed delays. Okay, so the answer is yes. Now, there's the balance one's got to form between artificial and neural. So the guys who created neural nets initially, perceptron, were actually based on the Huxley model. I mean, they were based on these biological models. But then what happened is they lost sight of the biology, and the neural nets went on their own path and created an entire field. So now you look at those neural nets, and the guys come in here and say, oh, these neural nets are not biologically motivated. No, they are biologically motivated. It's just that they did not evolve. They evolved in a direction different than the biology. Now, some people have basically taken spiking and have added to the networks. You've added plasticity to the networks where the weights change in a natural fashion. A few papers have come up across where they try to put a network of astrocytes, artificial astrocytes, where one astrocyte can actually modify multiple nodes simultaneously to get wider range of influence. I mean, it's maybe a false hypothesis, but a couple people have done that. So in the scheme of biological realism, constant delays is not realistic.
But what does it depend on? Does it depend on the...
It depends on the distance. Okay, there are two issues, okay? The axons have what's called a myelin sheet around it, and that controls the propagation speed. So propagation speed is a function of the length of the wire, the actual length of the path between axon, the helic, and the synapse, depends on the length. And presumably it depends on the properties of the axon. So all axons of a given length are more than likely, the spikes are not propagating at the same speed on axons, even if they are the same length. I'm guessing, but I refuse to believe that would happen. Because nothing's obvious in neuroscience. It's never the easiest
It's
solution.
related to the diameter.
Okay, right, you're right, I read that, yes. And in fact, the paper's written, I read that where they say the diameter and the spatial structure, some people hypothesize that it's actually done in such a way as to minimize wiring, because wiring takes energy. And so if you basically take a minimal energy approach, some people have come up with theories that say what kind of wiring is necessary, or what kind of speeds are necessary given the enclosure and given various constraints in order to actually get what we get. People play all kind of games.
So as you mentioned, the original neural net diverged away from the biology. How do you plan to diverge or measure your divergence away from?
Oh no, I'm not planning on. No, I'm not. Oh, you mean on the neural nets that we're going to do?
Yeah.
No, I'm not going to plan on doing that. The plan is to basically take a problem, like for instance, Synfire chains where everything's constant delay is too easy. The polychronous, we do the algebra, and then the next thing we try a model without plasticity, where we basically assume the delays are not constant and see what we get. If we get anywhere, then maybe we add plasticity, and then we can ask questions like, well, there's an exponentially high number of polynomous groups, based on what I've discussed so far. But now you could say, if you assume that they're related to memory, and that's an assumption, right, you could ask yourself, given the fact that the brain evolves, some polynomous groups are probably more stable than others. In other words, some are probably going to disappear under smaller perturbations than others. And presumably, if you will follow the hypothesis that the memories that we have, since we got memories, okay, and if they relate to polynomous groups, they clearly have to be stable polynomous groups. They can't just be completely unstable, otherwise we wouldn't memorize anything. There'd be an inconsistency. So one could conceivably analyze the stability of polynomous group to plasticity. So no, if basically one took a couple of students that took that and they became big shots and started studying that for 30 years, they would become an anachronism relative to what they would have learned on the biology in the meantime. But there's really no way around that. You start something and then you create an offshoot and then you hope somebody else will catch up eventually.
So I have a couple of comments. First of all, this 3-neuron primitive brain is more like a department chair's brain.
Yeah. Max, no, he's not. He already told me he had no brain, so he told me he didn't have to come to the
So
talk.
Max probably agrees with me.
Yeah.
Anyway, but the real point I want to make is that there's sort of two broad schools of computational neuroscience.
Okay.
And what you described actually illustrates some of it. The neural network started out with people who wanted to understand how the brain works, and then they realized that they could use the neural networks for computational purposes, and so, as you said, they evolved off in their own direction and became used for that purpose rather than to understand how the brain works. So, but basically that illustrates that there's people who are doing this in order to understand how to make computationally efficient systems, and other people who are trying to make biologically realistic models that provide for hypothesis testing, and then they try to improve the model in order to understand how the brain works.
Right.
And I think
Right.
that right now
Exactly.
you've got pieces of both in
Right.
yours, and I think that's great. So.
Yeah, and to answer your question, if you did something if you come up with an artificial neural net which is biologically more realistic, let's say, and we come up with some really cool concept involving big data, let's say, which he's talking about, okay? Then you can easily imagine that you get excited and then you move in that area and you lose the biology part. I mean, that can happen. At the moment, that's not part of our plan. The part of our plan right now is to stick with the biology, him more than me, because I like to stay in the middle. I'm much more of a computational guy. I never thought in a million years I'd be doing biology. Believe me when I tell you this.
So in your algebra,
yeah.
And this is sort of as a non-mathematician, I want to ask. It looks like to me that what you're doing is reframing the traveling salesman problem.
Oh yes, in fact, I talked to a graph theorist who's a colleague of mine that I did some work with in the past, and he said yes, it sounds exactly like that to him too. It's a problem like that, except not quite. It's probably related, and he said that the party is probably also related to event simulators of some kind. I'm not quite sure how, but the point is traveling salesman problem. You want to visit n cities and never retrace. In the case of the predicators group, it's the same only in the sense that it's spatial temporal. The traveling salesman problem, you're minimizing the path, but you're not minimizing the speed. Now, yes, the more general traveling salesman problem where you want to minimize speed, but it's still not the same thing because it's a case.
You're only considering the time delay, and so that's effectively.
No, view it this way: you got a traveling salesman problem. A traveling salesman problem has only one traveler going through a bunch of cities. The cities are the nuance. That's perfectly fine. Okay, so we thought about this, but now take two travelers. Let's assume we take two travelers. They leave from random cities in the country, and at some point, they meet at one city. Boom. Okay? Well, it's like saying from that city now, we're going to have that city links to 5 other cities. So now we're going to generate another 5 Mr. Smiths going to these other cities, right?
Well, I guess
Okay,
my point is that if you can do this right, the airlines will be a path to your door here.
Oh yeah, right. No, that's right. If you have an algorithm and then you could relate it to that problem.
Yeah.
Yeah, that's right.
No,
you're right. You're right. There are obviously other applications, and that's what we're all about in scientific computing. You want to take algorithms and apply them elsewhere.
Each airplane is an action potential.
Yeah, absolutely. Yeah.
And they all collide in Atlanta.
No, yeah, all kinds of problems like that. You could imagine at that level you could probably rephrase scheduling problems.
Right. So that was my.
Yeah, absolutely. So graph theory related, but the algorithms. Yeah, I mean, who knows? We have no idea what's going to happen here. It's exciting at the moment.
The airlines don't reproduce. The airlines don't reproduce.
Oh yeah, no, the current airlines don't.
So
By the time we get results,
five. You can't have 2 airplanes come in the airport and 5.
Okay, replace that by multi-missile missiles. Then we have the military, and those do exist. Okay, anyway, that's it. I got the whole